OK, so it's in case it's not completely clear, no food or drink. All right. All right. So I expect that everybody is quite tired by now. So I will try to somehow bring the level of abstraction down a little bit. And I hope there are no objections. So I'm going to talk about something that's the title of the lecture is Singular Support, or the first part of it. Specifically, this is singular support of coherent sheaves. And today I will only talk about schemes. So, and to begin with, so let me start with definition. So let's suppose that the scheme that I work with is an affine complete intersection. So something very familiar, hopefully. So the ground field has characteristic 0. So in other words, it's spectrum of an algebra A, and A is the quotient of another algebra by a bunch of relations, and this R is regular. So smooth. All right. Now, already here I said it's going to be very easy, but already here there are two versions. So if you can either do things classically, and then you have to assume that this is a regular sequence. So the classical way or if you, in other words, this is equivalent to saying that the codimension of this scheme, let me also call the big smooth scheme that contains this Z, I'll call it S. So either you assume that this codimension is equal to n, and then this is a complete intersection in the usual sense, or you drop this assumption, but then you really do need to consider this as a DG scheme. Fortunately, it's an affine DG scheme, so you just write explicitly, represent it explicitly by a Kazul resolution. So DG, no assumptions, but the setup is slightly different. All right, and here's a key observation, which is quite old by now. And in fact, in the first part of my, this talk, maybe this one, goes back to 74, whatever. So it's an observation about operations. So it's due to Golexan. Is that if you have, suppose that you have any coherent sheaf on Z, so just a finitely generated module over this algebra A, for now you can assume that it's an actual module, but I mean, really there's no difference here. So if you might as well assume that it's an object in the derived category. So recall that this is the category of derived category of complexes that have only finitely many non-zero cohomology groups, and those cohomology groups are coherent. So yes.
Can you say what does regular mean for the DG?
There's no D. No. Regular or smooth always means actual smooth. So R is always classical. It's the quotient that could be DG. So I want to say that if you want to write this quotient, explicitly, you can write for a Kazul resolution, so which will be a free resolution of A as an R module. And this Kazul resolution works even if you don't have a regular sequence, but then it gives you a DG algebra rather than an actual algebra. Does that answer the question? All right, so I was going to say that, just as a reminder, this is what in most classical books on algebraic geometry would be denoted dB-co. So, and then this key observation, I might call it proposition, although I'm not going to prove it, is that of course, the algebra A acts on F. And if you just think classically, that's it. There's no more you can say. But if you think about higher cohomological degrees, there are actually natural cohomological operations acting on F, but they have cohomological degree too. So they are actually, they sit in X2 from F to itself. And in fact, there are as many as there are equations for, so in this case, n. And moreover, they all commute. Now, I'm not going to prove this statement, but let me quickly say, at least explain, how something like this can naturally appear, at least one way how something like this can appear. So let me suppose that n is equal to 1. So it's a hypersurface, which is also very classical case. So, and let me denote by I this embedding of this hypersurface into the smooth ambient scheme S. So let me start with F and first push it forward to S and then restrict back. I don't know if I should write, like maybe for now I'll write explicitly that it's derived, but you might have noticed that everything is derived by default anyways. So because Z is given by one equation, such a thing can be computed pretty much explicitly using the Kazul complex. And from it, it follows that there is that it fits into an exact triangle like this. So this is from Kazul resolution. And now, well, if you can continue this exact triangle, there's a map between F and its shift. In other words, an X2 from F to itself, and this is the Xi. So this Xi is necessary if we want to, well, one thing that this Xi does is its cone is this push-pull object. OK. So you can also give a definition like this when there are more equations, but then somehow if you want to check that those operations commute, it's some work, but still it's not that hard. Yes? Well, I mean, really what I mean is that it's functorial in F. That if you have a map from F to G, then they commute. OK, so these operations were used by many people.
And the original Golexan just calculated X groups for the fraction field, for the radical field, something like that.
Well, no, I mean, I think that his key.
I almost remember this paper.
I think the key theorem of it, at least as I remember it, the key theorem, I'll state it in a moment. Okay. So, right. So. The key, well, let me state the key theorem, that let me consider the graded, somehow higher endomorphism ring of F. So, sorry. So let me consider not just cohoms, not just x2, but in fact all of those. So this is a graded, probably non-commutative algebra. But in fact, because it has these particular commuting elements, it's not just an algebra over A, but in fact, it's an algebra over A with this n variables added in. By the way, does this thing get in the way? Can I write here?
Yes, it can.
OK.
But
All right. OK. OK, so I'll try not to write below this. OK, so this becomes a graded algebra over this commutative graded polynomial algebra. Yeah, they belong to the center. This is actually related to the nature. It's stronger than naturality. It's somehow the derived naturality. But yes, actually, it is in the center. Well, I mean that when you talk about naturality, OK, if you're in the derived category to begin with, then it's equivalent. OK, or follows from naturality. Anyway, so this. OK, let me just recycle the boards. And so, at least from what, for our purposes, the main theorem of Golexan is that this algebra is in fact a finitely generated module over the polynomial ring. So it's a finitely generated a psi1 to psi n. And notice, by the way, that if you are very lucky, if, say, f has finite Tor dimension, so why is this non-trivial? Well, I assume that f is coherent, so in each degree, this thing is going to be a finitely generated A module. So if there are only finitely many degrees, then it's already finitely generated as an A module, so there's not much more you can say. And this will happen exactly when f is perfect. If f is not perfect, there will be infinitely many x for positive degrees. And somehow the claim is that this infinity actually all comes from action of these cohomological operations. That if you take those into account, everything is finitely generated.
This means that x2 is generated by psi1 psi n as an A module.
Did I say that?
No, I'm just asking, does it follow?
No. I mean, suppose it was smooth, then there are no cohomological operations at all. So then, of course, x2 doesn't have to be 0. So it doesn't. So it just means that somehow asymptotically, these are the only things that matter. That there might be a bunch of generators in finite degrees as a module, but then everything in higher degrees is obtained by those. By the way, this theorem is also can be proved by some kind of Kazul construction as well. So now, this was the key theorem. Now I can give the key definition, which was used by Varamov and Buchweitz, particularly when this f has finite length. And it's a special case of definition given in a paper by Benson, Ingar, and Krause. Oops. So this is in general. And the definition is simply, well, we now know that it's a finitely generated module, so let's look at its support and see what that is. So, and that's what I'm going to call the singular support of f is defined to be the support of this x from f to itself, but as a module over this polynomial ring. All right. So now, before we start, before I can say anything about it, what?
How much does it, I mean, is it true that in the right sense it doesn't depend on R?
Yes.
Do you want to say?
Not now. I will. Yes, I will. So, but let's look at it in these terms for now. So this is somehow maybe the most efficient way to compute it. Notice that by definition, it's what is it? It's a subset of the spectrum of this ring. So the singular supports, as I define them, they lie in the spectrum of this ring. But the ring was just obtained by adding some free variables. So this is basically the same z as before times a. So,
Excuse me.
yes.
As far as I remember, the degree of xi is -2 or something like that, right?
Yeah, the degree is 2.
Oh, okay.
Right.
So, according to what Dennis told us, as a topological space spectrum at the same place.
Right. So technically,
Something.
yes. Technically, I should be saying that when I consider this as a grade, I'm not thinking of this as a DG world. I'm thinking of it as a plain graded ring. So this X, I'm not thinking about the complex that computes it. This is just a graded ring, and this is just another graded ring.
So just a sort of trick doesn't seem to be okay.
Well, this is, I mean, there is this constant game about changing degrees, but I don't want to go into this. So, but, so by definition, it sits here.
2 is even.
Well, the fact that 2 is even is important, otherwise we wouldn't get anything interesting, right? Otherwise they would have to be nilpotent. So, right. All right, and so by construction, this is closed, this is a Zariski closed subset. And also because everything was graded, in fact, it's a conical subset. Conical subset. And I'm only going to think about it as a subset. I'm not even going to try thinking about any kind of any kind of scheme structure. So maybe I'll underline set. And another maybe simple observation is that we actually know what this conical subset looks like. So let me try drawing a picture. So there's Z, then we have this product of Z with the affine space.
It's
So
conical in this direction.
yeah, it's conical in the direction of AN. There's no, yeah. So in each fiber, you can say also that its intersection with each fiber is conical. And so you can now consider the intersection of this singular support with the zero section.
Don't you get some kind of conical because of the different weights?
No, but they all have weight 2. Yeah, so.
And we decided to ignore weights.
No, but I mean, I need to know that they are all equal. Otherwise, yes. Yeah, so what I was going to say is that because it's conical, its intersection with the zero set, with the zero locus is the same as its projection. So this is the same as projection onto Z. Maybe call it. But this just means that I look at the support of this as an A module. And so this is, in fact, simply the support of the usual support of F. So in other words, this notion is a refinement of the classical notion of support. So classically, support would be something in this, something here. And now at some points of this, now we're allowed at some points of the support to add some conic variety sitting over it. Okay, so notice in this example I almost did already a minute ago, or well, more than a minute ago, is that if F has finite Tor dimension, or perfect if you like, then this module, this graded module is bounded, which forces all those cohomological operators to be nilpotent. They cannot keep raising the degree if there's nowhere to raise past certain point. So this is bounded. Psi i's are nilpotent. In other words, that means that this singular support will be contained in the zero section. I'll just write 0. And conversely, to say that it's, so all of those arrows can be reversed. And this is one way to look at this notion, is that this somehow, the singular support is somehow supposed to measure the degree of imperfection of this F. So that it tells you at where it fails to be perfect, but it also tells you some directional information, that somehow it tells you something about directions, or maybe co-directions, if this is a word, in which F fails to be a perfect module. All right, so there are some natural properties that this module satisfies. So there are some, that this object, this singular support satisfies. For example, one exercise would be to show that it behaves naturally in exact triangles. I mean, the way you would expect support to behave. So maybe another exercise which somehow maybe a repetition of this point that this is a measure of imperfection is to check that if you remove the zero section, then this is not supposed to fill any perfect addition or subtraction to F. So in other words, this only depends on F as an object of the category of singularities. Well, I guess for this exercise to make sense, it's important to know what category of singularities is. But anyway, so only depends on F. Yes, modular perfect. So you can, so in other words, it only depends on the image of F in the quotient of coherent category by the perfect category. All right. So now let me move on. In fact, I'm going to start answering Sasha's question about a more invariant definition of this, singular support. So, and the way to approach it is by using what might be called shifted cotangent bundle. Call it bundle. And in fact, the claim is that this singular support actually, it always has to be a conical subset in this product. But in fact, it's far from being arbitrary. There are certain strong constraints that it might satisfy. As an extreme example, suppose that Z happens to be smooth. If it's smooth, then any coherent sheaf is automatically satisfies this condition. It's automatically perfect, so singular support is automatically 0. So we might have a whole bunch of equations used to cut out a smooth variety. So it looks like we refined the notion of support, but in fact we don't get anything new. It's still the 0, somewhere in the 0 section. And so a generalization of this, the claim is that for any f, the singular support of this module, singular support of any coherent sheaf, is going to be contained in the following locus. So x, surprisingly, is a point of Z. Maybe I can change it to 0 before it's too late. And these are the coordinates in the affine space. And these coordinates are supposed to give a non-trivial relation between the differentials of the defining relations of Z. So to remind you, Z was the 0 locus of a bunch of functions on a smooth variety. So these AIs have to be the coefficients that give a non-trivial relation. And in fact, this is the best estimate. In fact, the converse is also true, that if you have any conical Zariski closed subset of the right-hand side, it can be realized. It can appear as somebody's singular support. So now this right-hand side, this set, let me just call it the right-hand side, it actually has a following invariant description. So what is the right-hand side? Well, when we are talking about satisfying a bunch of this, you can read it as AI satisfying a bunch of relations. So we can explicitly, I can write it as follows. So let me consider this trivial vector bundle over Z. So degree n trivial vector bundle. And let me define a map from it using the differentials of f. This will land in the cotangent bundle to S restricted to Z. And the right-hand side is really the kernel of this map, but in a slightly weird way. We're talking somehow about fiber-wise kernel. Just think about it as a map from one vector bundle to another vector bundle, and then take the preimage of the 0 section. Now, in fact, this, I don't know, this arrow might look familiar, this image. This is exactly the derived version of the cotangent bundle. So this whole thing, this is the derived cotangent bundle to Z. So, or maybe another standard notation for this is the cotangent complex LZ. So indeed, the co-kernel of this map is the usual cotangent bundle. And so here we are looking at somehow the -1, at what happens to the cotangent bundle in degree -1. So in some sense, I hope nobody is going to mind if I write that the right-hand side is the kernel, is maybe the -first cohomology of the cotangent bundle to Z. The problem is that this -first cohomology is not understood in the sheafy sense. In the sheafy sense, this map might be even an embedding, but if it fails to be an embedding on a certain fiber, there will still be something interesting going on in this fiber. So technically, this is technically this can be constructed as some spectrum of I can just take spec of the tangent complex to Z. So if I want to write cotangent bundle, like functions on the cotangent bundle would be the symmetric algebra on the tangent bundle. If I want to get the lowest degree, I have to shift it by 1. And so I guess I need brackets somewhere in this expression.
The classical tangent bundle, yes?
Here, well, I mean, it has to be the something in the, so I mean the tangent complex. So you have to, so the dual of this. So I'm saying take this complex. So I'm trying to answer the following question. How do I write this without writing too many formulas? I'm still going to write formulas. So and the answer is as follows. Take this complex, dualize it, then shift it so that its top cohomology is in degree 0, and consider its symmetric algebra. If you want to end up with a classical scheme, let's also forget everything in negative degrees.
You take H0.
Yeah, you can take. I mean, as I said it, I even said so I'm supposed to take H0, or I'm really only interested in this as a set, really. Yes.
Is this now independent of the embedding?
This is the point, that it turns out, so this is a claim which can be explained in several ways, but probably not now, is that in this, if you use this definition, then singular support becomes independent of the embedding. So it's defined canonically as a conical subset in this object. So singular support of anything, let me just write it as, is canonically defined as a subset of this, of the right-hand side. Now,
The formula itself makes sense here, but you don't suppose that it's a complete intersection.
which formula?
Spectrum.
No, but the problem is that this will not sit in 2 degrees. So here somehow the point is that when you shift it and invert it and shift it, you will get interesting cohomology in degree 0, and then you get something in degree -1, but you don't care because degree -1 is going to be nilpotent anyways. So somehow it doesn't. If you're interested in this as a set, you don't care about nilpotence. So if this were longer, well, first of all, I mean, for classical schemes, it cannot be longer. But if you look at DG schemes, it could be longer. But then somehow you don't. Some of the nice properties actually rely on having complete intersection.
What do you mean cannot be long? If it's not complete intersection, but oh, I see that.
Yeah, I mean that it cannot be. If it's finite, it's 2 term. Right, this is
What's complete intersection in derived setting?
locally modeled on this picture. So locally cut out by a bunch of equations in an affine space, in a regular scheme. So in other words, I'm saying that, and there are equivalent definitions, but I think the most explicit way of thinking about it is that you start with S, which is smooth. Then you have a bunch of functions on it. So you have a map to, you might as well write a fine space. If you want, you can put something else here. And then you take the preimage of 0, which in the fancy language is this. So you take this fiber product. And
so when you say a function, you mean something that lives in degree 0, yes?
Yes.
So since you take fiber product in the derived sense, it means that you are joining odd variables.
Yes,
So
but I'm only allowed to adjoin, well, finitely many odd variables of degree -1. Yes. OK, yeah, so I don't know. I didn't finish this sentence, at least on the board. So it's canonical as the subset of right-hand side. Let me say it's canonical in the right-hand side. By the way, so there are more details on this in our paper with Dennis Gatesgory, which has singular support in the title. And in order to be consistent with this paper, I'll call the right-hand side just sing Z. So hopefully that's not going to be confused by the singular locus. It's somehow, although it definitely has something to do with the singularities of Z. All right, and notice, by the way, some similarity between this notion and the notion of singular support for D modules, if you're familiar with it. So in fact, that should hint where the name came from. And so somehow in the world of D modules, or rather holonomic D modules, there is also a notion of singular support, which is supposed to be a subset of the usual cotangent bundle. So it turns out that something like this also exists for coherent sheaves. However, it sits in a different cohomological degree. And for this reason, it's completely hidden when you work on smooth, when the base scheme is smooth. So if you work with coherent sheaves on something on a local complete intersection, then suddenly there's more than that you can say. OK. Now, let me turn the abstraction up a little bit.
Does this always exist for any, what I would call smooth DG algebra?
Why smooth DG? I'm not.
Smooth is like Koszul complex, or just finely generated.
In degrees, in all degrees, in degree 0 and 1? Or?
Infinite number of numbers.
But in this sense, why it isn't, again, what it? So
Notion of singular support.
I don't think you get a good notion that here somehow there's really this interplay that the degree 1, which is the first degree where things could happen, is also the last degree. So I mean, it's really tempting to see how much of this generalizes to non-complete intersections, but
do you know any example where you would actually need it for something?
where I would need such a generalization?
Yes.
I don't, but I mean, I know that whenever I give a talk, people ask this kind of question, so maybe they know. All right, so now let's move to this scarier object, this int_co. And so there was already some discussion about what this is, and roughly speaking, so just to summarize what was already said, is that there is a category So we have the category of quasi-coherent sheaves. This means the derived category of quasi-coherent sheaves, which is compactly generated by perfect complexes. And it turns out that there is a larger category Ind-coherent that's compactly generated by the larger category, generally speaking, larger category of coherent complexes. By the way, for now, I don't assume that Z is. I no longer for this. I can drop the assumption that Z is an LCI. And if I want, I also don't need any affineness assumptions. So, and as we saw, they might actually get in the way at some point. So, anyway, so there is this category. And in fact, there are several approaches to this category, some of them classical. So by classical, I mean triangulated. So there's an approach due to Krause, which realizes this category explicitly as the so this is the homotopy category of complexes of injective modules. I don't need it to be affine. I probably need it to be quasi-compact, quasi-separated. If for complete beauty, I probably want to assume that it's bounded, eventually co-connective, so that there are only.
But Krause probably worked with classical, right?
Yeah, Krause worked with classical. Yeah. But I don't think it's really important here.
The homotopy category in sense of C
Yeah.
space, right?
Yes, can I? So, but not, the important point is that it's the homotopy category of injective complexes, or complexes of injectives. Yeah, maybe so that I can avoid the discussion of what injective means in general. Let's say that it's classical. So, and this looks very much like a derived category. We know that object in derived category can be represented by injective complexes, but there is a crucial difference. Namely, if you want to work with the unbounded derived category, which we do, then not all complexes of injectives work. You have to restrict yourself to what is called k-injective complexes, which is an extra condition. And so this shows this somehow one way to see why the category of quasi-coherent sheaves is actually smaller than the category of ind-coherent sheaves. So this is the same thing for what is called k-injective, which satisfy certain extra condition. And also, by the way, in Nick's talk, it was mentioned that these two categories don't actually differ if you only look at things bounded from below. Well, that's familiar. If you look at things bounded from below, then you can use usual injective resolutions here. So there's no difference between this k-injectivity and usual injectivity.
Sorry.
Yes.
Well, you have a
Well,
joint functor, so
no, but one of them is fully faithful. The other one is colocalization.
So
Yes.
can I see the adjoint functor, this coefficient functor in this language?
That was kind of my point, that in this, of course it exists. You can write it, you can construct it. Well, it also, but in this picture, it's easier to see one of these maps, but harder to see the other.
On the level of complex,
yeah,
you
of
can
course,
Yes.
of course you can see both of them.
Right, I mean,
Homotopy category of k-injective complexes is also category of all injective complexes localized by
exact one. You kill the exact one, then you get the
yes,
smaller one.
exactly.
right. So that's true, actually. OK. So now,
So do you still think of them as infinity categories?
if you want, But somehow my point was that for this point we don't need to, that this is a very triangulated approach. Maybe I should put little triangles here. So this is triangulated. Of course, I'm writing myself into a corner because next I'll need to draw.
You apply Laplace iterated to Krauss.
Okay, there's one in the middle. So, but anyway, so there's also it's also equivalent to a construction of Pasicelsky, which is somehow funnily it's what it's called co-derived category, which is obtained by taking change the definition of the derived category by modding out by a smaller class of complexes, not by all acyclic complexes, but by a smaller class. So, and then of course it's if you mod out but by whatever remains, you get the usual derived category back. Now I have to put this 3 inside some kind of DG sign or a yes. It's true that the homotopic category, yes, that it's no. I mean, you can also make a completely triangulated statement that this is in fact compactly generated by coherent complexes. So if you have a short, if you have a bounded coherent complex, you can replace it by its injective resolution. Those will be compact in this category, and they generate it. Follows from what? Well, like everything else, yes. Okay. So, and then the way that already appeared earlier is that you can really define it as int completion of the category of this. The category of this coherent category. Now this, well, this requires, this actually depends on some technical things, as was pointed out. First of all, I mean, we need to make sense of what incompletion is. Secondly, this requires us to work with some kind of higher homotopy story, so we cannot work with triangulated objects. It has to be DG, infinity categories, whatever. But it turns out that somehow it's more, in many ways, it's more explicit than those two approaches. So, for instance, one nice thing is that it allows us to think of these objects. So, in this, under this third approach, we can think of int-coherent objects in two somehow complementary ways. So, this means that on the one hand, these int-coherent sheaves are formal inductive limits of coherent sheaves, co-limits. On the one hand. And on the other hand, we can also say that in order to measure an incoherent sheaf, we can sample it by mapping all possible coherent sheaves into it. So this is the definition that appeared in Nick's talk, that you can also think about this int-co as, I guess, as the derived category. Well, just, you can think of these objects as functors from the category of coherent sheaves into a category of vector spaces. Sorry? What? Well, exact functors, but I think when you're talking about derived category, they would have to be exact. Yeah, so from coh Z into vector spaces. And so it probably should be. Well, I should put op here, technically. But no, I don't think self-duality has anything to do with it. I mean, why would it? All right. So I'm going to use this point of view, so which means that from now on, I cannot. Up to this point, I could have worked with triangulated categories, and in fact, that's what I was doing. But from now on, it has to be the G world. And well, I guess 5 minutes of the G world is not so bad. So, and so
I'm sorry, I'm
Yes.
probably confused, but still, on the right-hand side, you have functors from coherent sheaves to vectors. It's a sort
Yes.
of Yoneda embedding,
yes.
right? So int objects are part of them. Or am I wrong?
No, but I mean, if I consider all exact functors,
Exact functors, this is
yes,
what makes
this is then you can, yeah, anything is. What? Yes, I have it now, but it's very small, and yes. All right, and so because of this interpretation by functors, because an Ind-coherent sheaf is completely sampled by mapping coherent sheaves into it, we can easily extend this notion of singular support. It somehow naturally extends from coherent sheaves to Ind-coherent sheaves. Because, well, we can, so given any f, so an Ind-coherent sheaf, so we can consider homes into it from all possible coherent sheaves. Now this cohomological operations will act on G, and therefore will act on such homes. And so I can ask about the support of the resultant module. And in fact, let me define the singular support of F to be the largest somehow thing that contributes. So it's going to be the union of, so I take home from G to F. I ran out of room. So let me, yes, it's very bad to leave this union. So it's the union of the supports of all the home modules. Should I write home GF? Maybe X GF would be, so it's the graded version of the X. But supporting this, taking these extra operators into account. Also, I personally find it psychologically easier to make support closed, so I will close this. No. I will take the closure, although it's not necessary, for example, in.
Excuse me.
Yes.
Defining single support of Ind-coherent sheaf
yes,
by using the notion of singular support of
coherent sheaves. Or, well,
X of GF.
well, I mean, okay. So using the using the cohomological operations on coherent sheaves. So is this? Yes,
So F is by definition some inductive limit of coherent sheaves.
that's right.
Just the union of the singular supports of those guys.
Well, but the question is, you can probably write it as an inductive limit in some silly ways, where you will get some extra stuff. So there is, in fact, a valid question of whether you can obtain an coherent. So there is always an inclusion in one way. So what you have to check is that is the following true? Is it true that you can always obtain?
What is the inclusion?
So the question is, suppose suppose f is written explicitly as a limit of coherent sheaves. Then it's clear that its singular support is contained in the union of singular supports of those guys. So
But you cannot expect this.
but in fact, it's true. But let me. I guess this will be the last thing I say. So it better count. So let's suppose that this f is written alpha, where alpha is where f alpha is a coherent sheaf. Then easy is that the singular support of f is in the union of the singular supports of these terms. And a non-trivial theorem, which in this case is actually also a special case of theorem of Benson in and Krause, which is that, in fact, if you choose f alpha wisely, you can ensure equality. I guess with maybe I need since I'm closing, I think I need closure of this.
Not to make them too big. You mean,
Yeah, that's what I mean.
Zero once.
That's exactly the point. So somehow the point is that if I'm only interested in, so what it says basically is that I'm only interested in incoherent sheaves whose singular support is restricted, then I can construct those using only coherent sheaves with the same restriction. So in other words, this is some statement of compact generatedness for a category of incoherent sheaves with restricted support. So I'll return to this point, I don't know, tomorrow, or if there are questions in the tutorial. So anyway, let me finish this sentence and then I'll be done. So we can choose f alphas so that it is inequality. And by it, I mean this inclusion. Well, I'm taking the closure just because that's something I do. I'm sorry, I didn't hear the question. I'm sorry, I'm still not sure what. So, I'm. Why? No, it is defined because xi's act on G. Yeah, it's not a finite. Yes. Yes. Right, but I think I'm using somehow the weakest one. So I'm taking the closure of. So the closure of all the other notions.
So this may explain why you prefer to take closure.
Well, the real reason why I prefer to take closure is that I'm only interested. I'm only interested in categories of the kind consider incoherent sheaf, require that its singular support lies in some closed subset. Right.
What is psi I in the definition of the singular support for the Ind?
Well, the same guys we used in the, so
Wait, since they act on
they act on G, and therefore they act on
do
this.
not act on, well, yeah.
Well, they do act. If they act, once they act on G, they act on.
We change. So, I mean, their definition depends on the coherent module.
Yes. So, but they are,
For each
but
G you choose.
no, but they are natural. There are. So, if you like, I have for each G, I have an operator psi1, which is an endomorphism of the identity, or a morphism from identity functor to identity.
Some canonical
It's completely canonical. It's not right.
Okay.
Then also to say x gx and x gx.
Yes. Any other questions? Why? All right. So
Maybe comment why this definition agrees with your original one when F is coherent?
Yes.
that's an exercise, but it's not. But it's not a very hard exercise. Basically, you need to check that if F is coherent here, then the support of this module cannot be larger than the. Somehow we're saying that the support of this module is largest when G is equal to F. By the way, you can ask the same kind of question in for usual notion of support. You can ask, okay, why is the support of endomorphisms of a module larger than support of home from this module to anything or from anything to this module? That's almost trivial. Any other questions? Dennis, what's the plan? What timing?
I think it's up to you. You said you would take the executive decision.
Yeah, but I don't have the schedule in front of me.
So
When?
when we were supposed to finish?
Yes.
The original. Okay, here are the important considerations. We were supposed to finish at 5:30 this talk.
Yes, and start next one at.
Here's the trouble. Okay, maybe I have to disclose this. They're gonna put up food. So at 6:30. Now I think it might be psychologically difficult.
6:30 or 7:30?
7:30. No, they said so it'll be out 6:30, and I'm afraid it'll be psychologically 7:30.
No, but the problem is this food will be here already. Okay. So, well, maybe we should agree that at 6:30 it's okay to leave because it's a tutorial. So,
Yeah, it's tutorial. I mean, it's always okay to leave.
yes.
But if you want to technical attend, I don't know. So it's
No, anyway, so 6 to 7?
fine by me. Just
Okay. Okay, so let's have a short break, and if you want to stay longer, that's fine too. And we'll start again at 6.